or sort of fallacy. Yeah. So the last day did some slightly more intensive calculations to look at fallacies, or what we call fallacies. Appears to be like fallacies when we talk about radiation. Okay. One was when the radiative reaction force was larger, so the F external was 0. Then there was a case where the acceleration was constant. And I also mentioned there's another interesting one where you sort of try to understand whether Newton's third law applies. So if you have a wave impinging on electron, the electron has a transverse motion, so it has a transverse momentum, but the wave actually has a longitudinal momentum. So to have an electron have a transverse momentum, there has to be something which should go the opposite way so that the momentum is balanced. Otherwise, suddenly you cannot get a momentum. So you have to have some balancing over there. So what happens over there? So that's another thing. Now, what I will try to do is that I will try to not work that out right now. First, I will go ahead a little bit with something else, and then if I have time, then I will go back into that. Otherwise, in the notes that I upload, I will basically have the notes for that transverse momentum and longitudinal momentum, that thing as well. Okay. It's just because you don't have enough time. We want to go ahead and rush through things a little bit. None of us wants to do another 10 classes, I guess, unless some of you are very interested. I'm getting tired, to be honest. So today we are going to, we have talked about radiation, and mainly we have talked about radiation in the non-relativistic limit, although sometimes we have mentioned relativistic limits and we have said that, okay, things change or not, but today, let us move from this non-relativistic limit and go a little bit about relativistic limit, because this is what will be needed when we go to the next topics. Okay, so we basically had in the case of one of these fallacies, we talked about electron going in circle, but then we'll see that we need to talk about it with the relativistic limit when the velocity of electrons is very fast. Okay. So let us go into the relativistic limit a bit and try to see what it means. Okay, so let's talk a bit about emission from relativistic particles. So obviously the particle moves with relativistic speed, that's obvious. So the charge moves with relativistic speed. Okay. What we want to do is we want to go to the instantaneous rest frame. So there are two frames, the frame at rest, which is K, and the frame which is attached to the charge, which is moving. Okay, so there's a frame which is moving at K prime, which is very fast. But we want to go to the instant, this K prime. In the K prime frame, if I have a prime frame which moves as fast as the charge, then in that K prime frame, the charge is instantaneously at rest. Okay, so we go to.
Sir, you are not sharing your screen.
Oh, again, sorry. Thank you for pointing me out. I did this last time also. Okay, so this is what you can see. So we go to the instantaneous rest frame, to the rest frame K prime. Okay. In this frame, the particle has zero velocity, and therefore in the K prime frame, we can apply the non-relativistic Lama formula. Okay. So for that instant, we can apply the Lama formula. Okay, this is what we can do. So we go to the instantaneous rest frame of the electron. At that time, there has zero velocity, and so whatever we have done previously, we can do that. So we can write down. Excuse me. We can write down W, which is the total energy emitted in time dt prime. Okay, and at the rest frame, the momentum dp at the rest frame is 0. Okay, so the radiation is symmetrical. Okay, so the radiation is symmetrical. Now, with respect to the K prime frame, I can think of the K frame to be moving at a velocity minus v, right? So prime K frame as velocity minus v. Okay. And so now it basically means my dw is gamma times dw prime. Okay. Also, dt, which is the time interval, and dt prime, that is also related by the gamma. My dt is also gamma times dt prime. Okay. So if I look at the total power emitted, therefore, the total power emitted, my P, which is dw dt, and which is basically gamma times dw prime by gamma times dt prime, which is equal to dw prime dt prime. So what I have is my P and P prime. This is the same, which basically means that the total power emitted is Lorentz invariant. So the total emitted power is Lorentz invariant. Okay. Now, which basically makes things easier because we know the Lama formula. We can use it at the instantaneous rest frame, and that gives you whatever it would be in the moving frame itself, right? So we have my P prime, okay, that was 2q squared by 3c cubed times the, right, it was the square of the acceleration. Now let us define something like, I will basically say it's easier in a book because you can write boldface over here and you cannot write. So this will be my 3 vector, but just a bar on top will be my 4 vector. Okay. So this is our definition. So now with this definition, we can write down the total power in terms of the 4 vectors instead of the 3 vector acceleration. So if you look at your 4 vectors, so this is something that you have done in the relativity notes that I gave you. Look over there. If I take the dot product of the 4 acceleration with the 4 velocity, right? This is du mu d tau, okay, times u mu, and so this is like half d tau of u mu, and so this bracket in the bracket is basically a constant. C squared is equal to 0. Now in the instantaneous rest frame, if I go to the instantaneous rest frame, so in the prime frame, so remember this thing. Now in the instantaneous rest frame, what we have is this is equal to 0 because it's not moving. So acceleration velocity is 0, acceleration is 0. And so what we can write is I can take this 3 vector, okay, this thing, write as a prime t times a prime t. Okay. This I can write as so I can choose whatever variable. So now you see something very interesting has happened. What we have found over here in terms of the 3 vectors, we can write this in terms of the 4 vector. So now with this, what we can do is that we can take this down like this, okay, and write my P as 2q squared by 3c cubed. Okay. So the power, the Lama formula, is manifestly covariant. So this is the, what we have is the where these A's are now 4 vectors, not 3 vectors. It is something that should be useful. However, even though we can write down the normal formula manifestly covariant, it's actually more useful to write this in terms of 3 vectors. So what I want you is, as a homework problem, is very short homework, and you would realize that this homework problem is very closely connected or very similar to one of the problems that I gave you for your exam. So what I want is that it is useful, let's say, to write P in terms of d2x dt. So physical distance instead of dx mu d tau. So it's good like this. And in this case, this is a 3 vector on the top. It's a 4 vector below. So show this result that you can write down your power to be 2q squared by 3c cubed into gamma 4 a perpendicular squared plus gamma squared a parallel squared. So I remember some of you were actually asking me, you're getting a formula which was similar to this, but in the force it is not exactly the same, it's slightly different. Okay. It's not over there, it is not a parallel squared plus gamma squared a perpendicular squared, not the way that I have written it over here. But I think maybe you have been using something like this. So where your A parallel in the power frame is basically your gamma cubed parallel, and your A perpendicular, the prime frame, is gamma squared A perpendicular. So this is a homework problem that you should do. Okay. Now what? So now knowing this, what we should next do is we should try to look at what this means with the angular distance. So over here, of course, we're looking at the total emission. But once we are moving with the relativistic speed, it turned out that the emission obviously will not be symmetrical and spherical. It will have a structure. In fact, you already know that emission typically has a dipole structure. In the Lama formula, the angle was a dipole, the sine theta squared structure was there. So we need to know what happens to the angular distribution when we have relativistic particles. So let us try to work out the angular distributions. So angular distribution of power. And obviously this is very important because whether you want to look at relativistic particles in an accelerator or in astronomy, you will always need angular distributions because you are scanning an angular space. And so you want to know what is the angular distribution of the emitted power that you get, or the emitted flux that you get. So look at angular distribution of power. So for that, we can draw basically in K and K prime frame. We can draw some, let's say, some area. Okay, this is in K frame. So theta is a d theta. Okay, it's dw. Also remember it's dp, and we have a K prime frame over here. This will have the thetas will change. Okay, so this is now theta prime, d theta prime, dw prime. So K prime is moving with the velocity v to the right, or in the instantaneous prime and K prime, then K is moving with the velocity minus. So your dw prime, okay, which is basically the energy which is emitted into the solid angle d omega prime. So dw prime is basically emitted. So because the particle is in the K prime frame, emitted energy into the solid angle d omega prime. So this d theta prime and this area gives you a solid angle, and your basically my dw prime is that emitted energy into the solid angle d omega prime. Okay, and if I look at my d omega prime, this is sine theta prime, d theta prime, d phi prime. Okay, this theta is basically direction with the x-axis. So theta prime is from the x-axis. Similarly, I can write down my d omega as in terms of thetas and d phi's over here. So your d omega will be sine theta, d theta, d phi. So if I define these two variables, mu as sine theta and mu prime as not sine theta, it has to be cos theta because I want it prime, then I can write down my d omega in terms of my d mu. Okay, so then my d omega will be prime d phi prime. Okay. Now energy momentum is of course a 4 vector, so we know its transformation. So next thing we need to understand is energy momentum is a 4 vector. So you can go back to your classical mechanics, not classical, your relativity notes that we gave over there. So we know how it transforms. So we know how it transforms. Okay. So you can go there and find that my dw will transfer as gamma into 1 plus beta mu prime dw prime. Okay. So this is how the energy momentum will transfer. These things are there already in your notes. So you should go back over there. If I remember right, I have done it. I have written it down over there. Okay. Now what we want to do is basically quickly look at what is known as the aberration formula, because that will be used over here. So I will just recap quickly an aberration formula. So if you look at U parallel between the prime and unprimed prime, then this is U parallel prime plus V over 1 plus V U parallel prime by C squared. That's one thing. And similarly, my U perpendicular, this is U perpendicular over 1 plus B U perpendicular prime over C squared. So if I take the ratio of these two, so if I define my ratio as tan theta, which is U perpendicular by U parallel, then this will become U prime sine theta prime over gamma into U prime cos theta prime plus D. Okay. So this formula is often known as the aberration formula in relativity. Okay. So your U is your the azimuth angle.
Sir, there will be a gamma in the perpendicular.
Yes, there is a gamma over here. Thanks. Now remember, azimuth angle phi remains unchanged. It's only in theta that there is a change. Now for photons, okay, your u prime is c. So I can write down cos theta is equal to cos of theta prime plus v by c over 1 plus v by c plus theta prime. Okay. So this is something that we use a lot because when you're looking at radiation, you have to look at photons, right? So cos theta is this, and so my mu, remember we are going to use this mu over here. So my mu is basically mu prime plus beta over 1 plus beta mu prime. If I differentiate, then d mu is equal to d mu prime over 1. So gamma squared 1 plus beta mu prime whole squared. And remember that my d phi is the same as my d phi prime. So now I can again write down my d omegas, which was the solid angles. So you know how the two solid angles pan out, how the bunch looks in the two frames. So therefore, my solid angle d omega is basically d omega prime over gamma squared into 1 plus beta mu prime. So put this back over here in this, where is it? In this equation. In this equation, which gives me my energy radiated in this solid angle as gamma cubed 1 plus beta mu prime whole cubed into so it gets one important formula for you. Okay. The power, remember, radiated is dw dt. So this is the energy. So how we define W, remember? We defined W over here at the very beginning. Power is dw dt, and W was the total energy emitted in time dt prime. Okay, in a solid angle. So my power over here, so my P prime over here is basically dw prime dt prime. So now we see how the power in one frame is related to the other frame. If we know how to connect these dt primes. So in one case, there will be a dt, in the other case, on the one hand side, there will be a dt, and the other hand side will be a dt prime. So if I have to connect powers, if we have to connect the powers, we need to connect dt to dt prime. Now, how do you connect dt to dt prime? Actually, the reason I have, you should basically say it's obvious, but it is not that obvious. Okay. So we have two options. Okay. We have two options in this connection. So there is one option Let me call it option A, where my dt is gamma times dt prime. So this is basically just the time dilation, right? This is like the time dilation. So the time interval in which the emission is seen in frame, it then becomes the emitted power k. So in this case, if I do this, then the time interval in which the emission is seen in k. This is how we are defined. So the emission, of course, occurs in k prime, but the time interval in which that emission is seen in k, that determines my power. And so that basically gives me my emitted power. Okay. And so let me call this P emitted. So again, try to understand. So we have power, we know how the power or the flux over here, dw d omega is related between these two. But to know the power, you also need to know at what time this energy was emitted or what time this energy was received. So if we use this formula of time dilation, then we know what is the time in which whatever was emitted over there was received. And so this is the time interval in which this emission is seen in k, which is related to the time interval in which it was related in k prime by this gamma factor. Okay. And so this is the power emitted. I could have named it a little differently also, but this is what the k prime is. Now we can have another option also. So we can talk about another option. Okay. In this case, my dt has an extra term. So this is gamma times 1 minus beta mu dt prime. So this you should recognize, because over here we are also trying to figure out the fact that in one case the source is moving away. So what we have is this formula for relativistic Doppler effect. So in this case, the time interval, okay, of radiation received by the stationary observer in k, okay, but there's this extra 1 minus beta mu because the source is moving away. So I can now call this P received. Okay, so power is that what we observed. The question is, which one do we take? Okay, should we, in our calculations, should we take this or should we take this? There is, to be honest, for a long time, there was confusion and people have argued on both accounts. Finally, there is a consensus that what we should take is, as observers, we should take P received, and that actually gives you the right answer. So think of an astrophysical object. No, whatever, gamma ray burst over here. That is moving away because that object is moving away. So we should not only take into account the fact that there is a time delay like this, but we should also take into the fact that the object is moving away, because we as observers are sitting over here and receiving that power. So what we should take is P received is the natural thing to take. However, you should also figure out that suppose you have a lot of sources. So on the average, it will turn out that these two will be the same, because something coming on, something going. So if you have a case where there is a cluster where things are moving up and down, something is giving something, then these two things will cancel. These two things will become very similar. There's one more thing is that if I change in the second one, there is a what are called so the second case later you'll see will lead to some kind of a symmetry. Okay, that symmetry will come when we'll try to calculate some beaming and some relativistic stuff. So we'll come to that. So in this case, in this Doppler case, remember what happens is that your frequencies also change. Okay, so remember in this Doppler case, this Doppler effect case, there's also this frequency between emitted and theta. W prime is W comma 1. So power in K. Now, if I put this two formula, okay, in over here, dpd. So over here, I put that divide by dt and connect the dp dt. So dp d omega on both the sides. Okay, if I connect this, so basically put this and put this together, then you will see that my dp emitted d omega, this will become as gamma square into 1 plus beta prime. This will be cubed. So this is how the emitted power will be emitted. Similarly, if I want to look at the received power, this will have 4 with this is going to there's a So one thing, as you can notice over here, is that the second equation has a better choice, which is also symmetric. So if I interchange the prime and unprime and also change the velocities, the equation remains the same. Okay. And as I said, it is us, we observers, that we basically observe, stationary observers. So we are actually should be interested in whatever we observe that can be related to the power that we observe. And so from there, we can calculate the rest of the stuff. So we can know about the source by basically equating the left-hand side to whatever we are really observing. Okay. So if you have a telescope, whatever power the telescope observes is basically this thing. Okay. So this is what is used. Okay. So as I said over here, if you look over here, there's a symmetry between k prime, beta, k minus beta. So these kind of formulas are often, very often used in, as I said, astrophysics as well as in particle detectors. When you have a particle and you have detectors and all around, and obviously you want to look at which region of the detectors are collecting photons, and from there you basically give an idea of your particles, because all these things will be connected. Now, once we are sort of agreeing that this is what we are going to receive, then using this, we should also be looking at the radiation pattern. So use this to also look at radiation pattern. Okay. So we'll of course simplify that in the particle frame, the radiation is isotropic. That's the simplification that we use. If you don't want to simplify things, more complications will come. So initially we start with, because at instantaneous, the particle is at rest, so it's radiating isotropically. So simplification that we use is in the particle frame, the radiation is isotropic. Okay. Now, in the observer's frame, and this we have said again and again when we were having these classes on the special theory, in the observer's frame, this radiation will be peaked. Okay. So suppose things are very relativistic. Suppose beta is approximately 1. In that case, your mu, which is your cos theta, this is 1 minus theta squared by 2, and your beta half. Now, as you can see over here, beta has this relation with gamma, and it basically tells you that if I put this back over there in the previous formula over here, then what we'll have is that I have a 1 over gamma to the power 4, 1 minus beta mu prime to the power 4, and this in this case will be like 2 gamma over 1 plus gamma squared and theta squared will come from this mu, theta squared, this whole thing to the power 4. So this radiation, if it has this kind of structure, this, as you can see, is sharply peaked at theta equal to 0. So this is theta equal to 0. And its angular distribution, in the sense where the maximum of the flux is limited by a cone which has a angle which is 1 by gamma. Okay. And its angular distribution is limited within theta of equal to 1 by gamma. So that's something for the very relativistic case. Now, if you go back to the Lamar's formula, remember, it has a sine squared theta dependence. Right? So if I go back to my Lamar's formula, which is my dw dt d omega, which is q squared by 3c cubed u dot squared, and then there is a sine squared theta. Okay. So to do that, let me actually draw a figure. So what I have is, let's say this is x, and so oh, it is not. So this direction is v. This is, then I also want to drop off on the xy plane. I hope you figure out my drawing. So let me call this as phi prime. Okay. This is the direction of v. This is the direction of a prime is b prime, and the angle between the radiation, this is theta, small theta, and this is the angle between the acceleration and the radiation direction, which is capital theta. So the Lamar's formula, this is how you relate. Okay. So over here, the angle between the acceleration and the radiation is your theta. Okay. So this is the, anyway, I don't have to write, you can see it over here. Now, your acceleration itself, you can decompose into parallel and perpendicular. So what we can do is that we have my acceleration, which is acceleration parallel plus acceleration perpendicular, and use the homework that I gave before. So use the result from there, and then you will see that my dp d omega, which is basically this thing on the top, is your q squared by 4 pi c cubed, and then I have a gamma squared a parallel squared plus a perpendicular squared over 1 minus beta mu prime 4, then sine squared theta. So why I'm doing this? Because at the end of it, I want to come to some very simple results over here. So this theta over here must be related, to the angles in general, this theta over here must be related to the angles, okay, in K-frame. So in general, for any arbitrary direction of acceleration, velocities, this is a complicated thing. So velocities and accelerations has some directions, and you have to do this. So it's not really complicated. So it's complicated. Okay, so that is actually complicated. I mean, you can work it out, but you cannot do it analytically. Okay. So we take some simplifying special case. So we take a special case. So take special case. So basically what we're going to look at is what happens when the velocities and accelerations are parallel to each other, and what happens when the velocities and accelerations are perpendicular to each other. Okay, so take some special case. The first one we want to look at is what happens when the velocities and accelerations are parallel to each other. So case one is your acceleration is parallel to velocity. So when acceleration and velocities are parallel, then this A is along V. So your capital theta and your small theta are the same. Okay. So your prime is equal to theta. So sine squared theta prime is equal to sine squared theta over gamma squared into 1 minus beta mu. And your A perpendicular, of course, in this case is 0. Also, A perpendicular is 0. Therefore, you go back and you can write down your equations over here. So dp parallel d omega. This becomes q squared by 4 pi c cubed. A parallel squared sine squared theta over gamma squared into 1 minus beta mu. There is 6. We want to simplify this even further to finally look at what happens for these relativistic particles. We'll come to that in a moment. What happens when your acceleration is perpendicular to velocity? Okay. In this case, so your acceleration is perpendicular to velocity. So we have to relate, to do that, you have to bring in my phi prime also now. So just look at this figure and you will realize that in this case, my cos theta prime is sine theta prime cos phi prime. And again, you go back to this whole calculation over here. So my parallel is now 0. Okay, so everything is in terms of A perpendicular. So now we'll have my dp perpendicular d omega. This is q squared by 4 pi c cubed A perpendicular squared, okay, into 1 over 1 minus beta mu 4. This thing into another big relation, which is sine squared theta cos squared phi over gamma squared into 1 minus beta mu squared. Now this will be simplified even more in one more step, and so just bear with me in one more step. So this is one big relation that we get when acceleration and velocity are perpendicular to each other. But remember, the whole thing that we were doing till now was we wanted to look at relativistic particles. So when we wanted to look at relativistic particles, it's good that we look at the extremely relativistic particles. At the end of it, we are looking at photons coming to us. And also we want to look at some cases which is of interest where things are really relativistic. For example, when we have gamma ray bursts and in astrophysical situations, things where this so supernova burst or whatever, everything is like almost the speed of light. So we want to get to extremely relativistic situations. So we want to look at, so we further, we want to look at extremely relativistic velocities. Okay. So then my gamma, this is much less than 1, and my 1 minus beta mu is also very, very small, is very small, okay, in the forward direction. So I can write as 1 minus beta mu, this thing. This is basically go back over here. We wrote this 1 minus beta mu before. Okay. We'll find out. This we'll see comes in terms of the thetas, which is 1 plus gamma squared theta squared over gamma squared. We'll end up with this formula. Okay. This, as you can see, again peaks when theta is within 1 by gamma. So when theta, because gamma and theta comes together, so when theta is less than 1 by gamma in that region, it peaks. So it peaks, this thing peaks when theta is of the order of less than 1 by gamma. So now, finally, what we can do is that we can put these things and write down the two equations. There will be two big equations, but there is two important facts to it. We can write down, so putting it all in, putting all together, we get these two equations. One equation is for dp parallel d omega. Okay. This, as you can see, has a very high power of gamma, almost gamma to the power 10. Okay. And then there is some constant, 16, a parallel squared over pi c cubed, and then there is a gamma squared theta squared over 1 plus gamma squared theta squared, so to the power 6. Similarly, if you write down the dp perpendicular d omega, this has less power. It is less power in the sense like if you change your velocities, the rapidity with this changes less because it's gamma to the power 8. It is 4 q squared a perpendicular squared over pi c cubed, and over here is 1 minus so big expression, so I have to write it up, look it up. Hold on, just a minute. Yeah. Plus gamma 4 theta 4 over 1 plus gamma squared theta squared over 6. Now, this equation might look some big equations. I mean, what the hell? I mean, you have written down these equations, but these equations, these two equations, are very, very instructive if you want to plot it. And that actually tells us how your radiations will actually look depending on which directions you're going to see it. So let me do that plotting and sort of finish today. So suppose you have this dipole radiation. And over here you have your X prime. The particles rest frame. So this is at particle rest frame. So this is how the particle is instantaneously radiating. This is the radiation. This was what was the Lamas formula. But of course, we won't be getting this. We will be. So this is something one can ask an interview question just by reasoning without knowing the formulas. What we'll be getting over here is, if I look in this case, okay, where over here the acceleration, so this case A over here is acceleration parallel to velocity. So in this case, in the observer's frame, what we find, so this is now X, is we do not find this beautiful dipole pattern like this, but both are obviously boosted very much in the forward direction. And what we find is something like this. Okay. So this will be 1 by gamma. So this pattern that we see must be related to the original pattern. Remember, when we are trying to analyze pulsar beams, radiation from pulsars, so things are moving and every time it is coming here. Over there, you will get patterns from which you have to deduce what was the initial pattern. So this is one of the reasons. So this is the kind of things will come. Then one can look at the other case where the acceleration was perpendicular to velocity. Okay. So over here, this is X prime. And over here, the dipole pattern is different. Okay. Acceleration is perpendicular to velocity. Remember, in the Lamas formula, the dipole pattern, the theta prime, the big theta, how is related to the direction of acceleration. So over here also, in the rest frame, so in the particle frame, the dipole pattern is not this. Okay, the dipole pattern is not this in the particle. Over here, the dipole pattern is actually this. Over here, this is my big bang. And in this case, as you can see, again, it will be boosted, but your boost will be slightly different. So in this case, now my boost will be slightly different because there is a forward lobe and there is a backward lobe. Okay. And this forward and backward lobe will have different kinds of boost. So the forward lobe obviously will be boosted more. The backward lobe will still have some memory. And so in the observer's frame, what will happen is that this is X. And now we'll have this. So this, the previous one itself will become elongated. So the right hand side will become elongated. Okay. But the left hand side over here, depending on what is your angle, will be preferentially boosted on the plus axis. So the behind thing will become like this. And so the radiation pattern that you will find, if you have some very relativistic particles where your velocity and your acceleration are perpendicular to each other, will be this radiation pattern. So now, in a sense, we can match radiation pattern observed with the properties of what is happening at the source. And these things are often used, as I said. Your radiation patterns gives us important applications. You design your stuff by looking at radiation patterns. If my camera or whatever I call my telescope was facing from this side, you will get a beam over here, but you get side lobes from this kind of stuff. Okay. So all these things have to be kept into account when actually people work out radiation patterns, and then basically from there try to talk about the source, physics of the sources. So that's all I wanted to talk about, and I did. This is actually simplistic treatment. I did not do it in great detail. We will talk about this angular patterns a little more mathematically in the next classes, I guess, and so that we can connect those two with real life examples of, let's say, Cherenkov and synchrotron radiation. And then what will happen is that this slightly simplistic treatment of today with the treatment that we had yesterday, where we really use Bessel functions, these two things will come together. Okay. I don't know. The whole point of all this thing is that sometimes it's not possible to remember everything. I don't remember everything. No one does, or know all the calculations. But if the basic ideas stick with you, then those are very important. So small things that you remember, that this beaming effect, what happens when things are parallel and when it's perpendicular, this kind of basic things is there. Or when you used Bessel function last time, the trick of this Bessel function is used again and again, very, very effective. But the small things you just you keep inside you, then those things will help you over your time of as a physicist. Don't know when you will use it. Sometimes you will use it. So all this while there's different things we are doing. Okay, so we'll stop over here, and we'll again pick up next Wednesday. So next week, Monday to Thursday, there's TI for interviews, and I'm hoping that we'll have the Wednesday class. If not, I will let you know. Also, it may be that even if you have the Wednesday class, you will have a different Zoom license. So try to get a Zoom license. I'm known for definitely that I'll be in the interviews on Monday and Tuesday. Till now, I'm not on a Wednesday interview. So I think I can take the class, but if something happens, I will let you know. And in the meantime, please decide on your topics. Send me your choice so that you can get into it, because most of a large portion of your marks will be on your seminars. So I want you to do it as seriously as possible. Okay, so we'll stop over there.
Can I send the topic name on the Moodle?
Send me, you can send the topic in the Moodle, but best to send